Morning, everyone. In today's lecture, we are going to cover the topic quantization. In the previous lecture, we have done sampling. So, for a digital system, we need to have sampling first, then followed by quantization. Then we do encoding, and then it is sent to the channel. And on the other side, the process is reversed, so, which I'm going to cover in the later chapters or the lectures. So, in today's lecture, first of all, I'm going to explain what is quantization. So a digital signal is superior to an analog signal. That's why we are converting an analog signal to a digital signal, because it is more robust to noise, means it has more ability to can say cope up with the noise present in the communication channel and can easily be recovered, corrected and amplified. For this reason, the tendency today is to change an analog signal to digital data or digital signal. A continuous signal such as voice has a continuous range of amplitudes, and therefore its samples have a continuous amplitude range. In other words, within finite amplitude range of the signal, we find an infinite number of amplitude levels. However, it is not necessary to transmit the exact amplitudes of the samples, because any human sense, eye or ear, as the ultimate receiver, can detect only finite intensity difference. This means that the original continuous signal may be approximated by a signal constructed, this is constructed here, of discrete amplitudes selected on minimum error basis, and that error we know at the transmitter side, so we can correct it on the receiver side. I'll explain you what do you mean by error here. So the existence of a finite number of discrete amplitudes levels is a basic condition of digital modulation. So as I explained you, we have an analog signal which is a continuous time in continuous time domain, or it has a continuous amplitude value. We do sampling first, which we covered in the previous lectures, and then after getting samples, we are basically changing that signal to discrete time values. Means now my signal is defined at specific times intervals only or points only. And after that, we follow quantization. After quantization, the signal is basically a digital signal. It can have discrete time values, and then we do binary encoding of that signal. So what we do here is that we convert each quantized values into a binary code word. So quantization is basically a transformation which maps elements from a continuous set to a finite set. Three processes in analog to digital signal conversion. In order to process the sampled signal digitally, the samples values has to be quantized to a finite number of levels, and each value can then be represented by a string of bits. So what we do is that we have infinite range of amplitudes. So we reduce those infinite range of amplitude to certain amplitudes, which is decided by a transmitter and receiver, and then those amplitude levels are changed to the string of bits. To quantize a sample value is to round it to the nearest point among a finite set of permissible values. Hence, a distortion will inevitably occur. This is called quantization noise or error. So basically, what we are doing is that, suppose my signal value is, let's say, from 4 to 4.5. So I will make a rule that whatever the amplitude levels between 4 to, let's say, 4.4 will be, I will consider it as 4 only. And whatever the amplitude levels, let's say from 4.4 to 4.9, that will be considered as 5. So basically we are introducing a noise there, or we can say we are introducing an error there, which is known to the transmitter and receiver. So then we have both sampling and quantization result in the loss of information. The quality of a quantizer output depends upon the number of quantization levels used. So more the number of quantization level, the better the quality will be. The discrete amplitudes of the quantized output are called as representation levels or reconstruction levels. The spacing between two adjacent representation levels is called a quantum or a step size. So we have this sample signal. So it is defined at a different time instance with a gap of sampling time, and we are getting a discrete time signal. So basically my original signal was like this. Now that signal is converted to signal in this form. Then what happens is that we have a signal levels defined in this form. Let's say my maximum value is V max, minimum value of amplitude is V minimum. So basically if I make a staircase from this, then it will be something like this. It goes like this and comes like this. So this is defined as my quantization error or the amplitude levels which we are doing here. So let's say I'm defining my V minimum as 0, 0. The next level is considered as 0, 1. So basically if the amplitude levels are within this range, negative side, then we will consider this as 0, 0. If we are representing the signal by 2 bits only. Then next level here is considered as 0, 1. This one as 1, 0, or you can say 0, 1, 2 are the levels which are 3 are defined. So quantization signal, or we can say it as staircase waveform. Now, how to get the value of step size? Step size or the region width, delta is basically separation between two consecutive quantized levels. So it is the difference between these two levels. So delta is equals to V max minus V minimum divided by L, where L is your number of quantization levels. So if number of bits which we are using for the signal to be defined, then this L must be equals to 2 raised to the power n. So if you see here, my n is equals to how many bits we are using? 2. So n equals to 2. So L is equals to 4. And you can see that we have 4 levels here. 1, 2, 3, 4. So this is defining the number of quantization level. L is equals to 2 raised to the power n. In terms of dynamics, suppose this is an amplitude with defined potential levels. But if it's not defined, then we can use dynamic range, or we can say voltage peak to peak value divided by L. Now, if we need to find the value of your quantization power, so the first thing which we need to define is your quantization error. So quantization error is basically sampled value, quantized value is equals to plus minus delta by 2. So it's always lie between delta by 2. It's not going to be greater than delta by 2. Whatever you are changing the value, amplitude levels are, they will always lie within this range. So this means that the maximum possible value of Q is equals to plus minus delta by 2. Now we have two types of quantization. One is your uniform, another one is non-uniform. In uniform also we have a mid-rise type, and another one is your mid-thread type. So I'll explain it. Uniform quantization means that quantization levels are uniformly spaced. Means these levels are uniformly spaced. It's not like that we are going from this level to this directly. Means there's a uniform gap between them. Like I'm raising from 0, 0 to 1. So it's basically 1 bit difference you can see here. Or in a similar way, you can say in terms of amplitude levels is 0, it's 1, 2, and 3. So it's uniform. Whereas in non-uniform quantization, the quantization levels are unequal, and mostly the relation between them is logarithmic. We are basically going to cover only uniform in this course. Now, we have two types of uniform. One is your mid-rise type. So mid-rise type means you will start from 0 and then whatever the range here is, start from middle of it and go up in the staircase. And in the mid-thread type, the quantization starts from the middle of the first one, not from the origin, and it goes up with the same, can say, time difference as we were using here. But the difference only lies there from where they are starting. So there's one more thing which you need to note: the more zones, the smaller delta, which results in smaller errors. So if our quantization levels are more, the value of delta is less, which means that the quantization error is less. If delta is sufficiently small, then quantization error can be assumed to be uniformly distributed, random variable when the error may take on a sample value QE anywhere inside the interval thus. So the value lies between this value, as I explained you earlier also. Under these assumptions, we may determine the average power of the quantization noise by averaging QE square over minus delta 2 by 2 plus delta by 2. So if we need to find the average, we will take the average over QE square. So if you know how to find the average, you need to divide it by the interval. So that complete interval is delta, and you integrate it within the interval. So it's from minus delta by 2 to plus delta by 2 QE square dQE. So then it will become QE divided by 3 delta by 2 minus delta by 2. When you will put the value of QE, and what is QE is here, and in place of QE it will be this delta. So then it will become delta Q by 8. This will become minus of minus delta Q by 8. When you will add them, it will be delta square by 12. Why 12? Delta square by came here because there's a delta here. The cube will be cancelled and it will become a square. Now, if you need to find it with the help of probability density function, I don't know whether you know it or not. There's a probability density function where you use PDF to find this. Then PDF is equals to 1 divided by delta in this range, when the QE is in this range, and use variance of error is your mean square value. So it's QE square FQE into DQE. Expected value then will be E, can say expected will be E QE square, and then it will be equals to delta square by 12. This is again the different mid-thread uniform quantization levels. So the mid-thread type is so called because the origin lies in the middle of a thread of the staircase like graph. So it starts from here, delta by 2. If n is the number of bits per sample, then the quantization is equals to 2 raised to the power n minus 1. Why 2 raised to the power n minus 1? Because it's not starting from 0, it's starting from delta by 2. And overload level, because it starts from delta by 2, it leads to an overload on the system, is equals to L into delta by 2. So it is basically, it is limit of quantization error. Input signal should be within L delta by 2. So for n equals to 3, L equals to 7, odd, and overload will become 3.5 delta. Mid-rise type is so called because the origin lies in the middle of a raising part of the staircase graph. So n is equals to bits per sample, and it starts from 0. The quantization levels are n. So L is equals to 2 raised to the power n, and overload is again same, but now it's an even number because we don't have a difference of delta by 2 in this one.